Hey, today it's section 6.4, and we are going to look at torque and finding centers of mass and balancing points and centroids and that sort of thing. This is the application that we're going to look at today, and we use calculus to do that. You can think of like this. We could think of this pen as like a rod, and we would be interested to figure out where it is that it balances. And I can't actually get it to balance at all, but in case you may notice that it's not going to balance exactly at the middle, and that's because it has like some different, this is actually a pen, a special pen used for this computer, and so it has some probably electronics in one end of it which makes it more dense. So where you balance it is not necessarily at the center. So I always think of, I used to have this toy and I wish I still had it. It was like a eagle, and it was plastic, and you could put your finger right on its beak, and it would look like it was flying. Have you ever seen those kind of toys? You know, so that's the idea of the center of mass or the balancing point. That's kind of what we're looking at. Or you don't really see these very often anymore either, but like a seesaw. And you know, if you're depending on your weight, if you want it to just balance evenly, one person may need to get closer to the fulcrum, which is the balancing point, than the other people if you wanted it just to be steady. Because if you both sat at the same side, one person may always be lower, right? So we'll look at, that's the application that we're going to look at today. And again, I was looking at these OneNotes. The video will probably be pretty good of it, but the notes themselves, I still need to work on getting them to where they're legible if you're trying to write as you're going. So you may just want to kind of view this, and we will see how that goes. Okay, so I can make this bigger and easier for you to read. So I just stole some stuff out of the textbook and posted it into your notes. And so just to get some definitions and to get our mind around it. It says, we develop our mathematical model in stages. The first stage is to imagine masses, and these are the masses, M1, M2, and M3, on a rigid x-axis supported by a fulcrum which is at the origin. Okay, so and each one of these is going to have assigned distance away from the origin. You know, like this may be 1 unit, this may be 5 units, this could be -3 units or something like that. And the fulcrum is at the origin. Now each mass exerts a downward force, which is just the mass times, and this is some physics, you know, a force is the mass, and then also the gravitation multiplied by a force equals mass times acceleration. You may remember that, Newton's laws. And so you take the mass, and the acceleration due to gravity is what's pulling it down. And so it's a downward force, which is mass times acceleration due to gravity. And each of these forces has a tendency to turn the axis about the origin the way you turn a seesaw. This turning effect is called a torque, and it's measured by multiplying the force, which is, of course, mass times gravity, by the sign distance from the point of the application to the origin. Masses to the left of the origin exert negative counterclockwise torque, and masses to the right of the origin exert positive, or what they consider clockwise torque. Okay? So the sum of the torques measures the tendency of a system to rotate about the origin. And in the textbook, they actually show you like the planets, you know, the way that they rotate and their tendencies has to do, you can think of this based on the mass of the planets and their center, which, or the fulcrum, which in terms of the universe or our system is the sun, is the center. Okay, so you have this idea of torque. Again, torque is the turning effect, and it's mass. It's the sum of the masses, or sum of the force times the distance that it is from the center, and you add those all up. That's your system torque, and the system will balance if and only if the torque is set to 0. Okay, so since G is common to each of those, we can factor the G out, and we get this right here, M1 X1 plus M2 X2 plus M3 X3. This is a feature of the system, and we actually call this right here the moment. Okay, we use the word moment to describe what this is. I don't know why they used moment, but they did. Okay, so the torque is a product of the gravitational acceleration, which is a feature of the environment in which the system happens to reside, and the number m1x1 plus m2x2 plus m3x3, which is a feature of the system itself, is a constant that stays the same no matter where the system is placed. Okay, so this sum of the mass times the signed distance, the individual mass times the signed distance, is called the moment of the system about the origin, and it is the sum of the individual moments. So m1 times x1, that's the individual moment, m2 times x2, m3 times x3. Okay, and so we have this notation that the moment of the system about the origin is just the sum of the individual moments. And this is the concept, remember, one of the best applications that calculus gives us is whenever we're summing a bunch of stuff, that's really just like integrating if you have a function. So that this summation concept should lead you to the thought that we'll be integrating later in the lesson, which is correct. Okay, so this is kind of a fun little exercise that they do right here. It says we usually want to know where to place the fulcrum to make the system balance. That is, at what point do we put the green, the special fulcrum so that the torque adds to 0. So we no longer want it at the origin. We want it to balance out. And so obviously if you're on the seesaw, you have to move yourself. You are the M1 and you move yourself. But in this picture, what they're doing is they're actually moving the fulcrum, the base of it. But you know how seesaw, it's kind of like that thing's cemented into the ground, so you have to move yourself. Okay, so they call that place x bar, where the torques add to 0. So you have it balanced, the x with a little bar on the top of it. Okay, now they just kind of work through the algebra here. They say the torque of each mass about the fulcrum is the special location so the distance it is from x bar times the downward force. So if x bar is our special location where it balances, if we figure out this distance times the force, we add them all up and set them equal to 0, we will be able to solve, and what we're going to do is we're going to solve for x bar. Okay, and we're just watching this. We just have to do this one time, just kind of watching it. Okay, so the first thing they do is factor the g out of there. Okay, and because you're allowed to do that, and then we can divide the g out, and we can see that the pull of gravity doesn't matter. It doesn't matter in this situation. So the g is divided out. All right, and then we can sort of, I don't really want to say it, but we can kind of use a distributive property here and distribute this summation sign through. So we have the sum of the moments minus the sum of x bar times the m, which is just the mass itself, okay? Just the masses, the sum of the masses. Now, this summation symbol would go from k equals 1 to however many masses you have. So each of these little pieces, m sub k, x sub k, would be dependent on, like if you're at the first one, second one, third one. But this x bar it's a special number. It's a place. So it can be factored out of that summation symbol. So that's what they do in this next step. They move this summation over and they factor the x bar out. And then in order to solve, I think you might be in DMAC 108. I'm not sure. This is not educational psychology. This is Calculus 2. So I think it's a different classroom. Okay. So what we do here is we will...
What? You said 108?
I really don't know. But
that's 110 on here. Is there another 110?
No, this is it. But if you go, several people have been looking, and I've sent them to the University Center, so I bet maybe somebody there will help you.
Okay.
It's just down the hall.
Okay.
Sorry for that. Okay. Here, what you do, you can solve this for x bar, and you can see that it is just the sum of the moments divided by the sum of the masses. Does that make sense? The sum of the moments divided by the sum of the masses. Okay, and so that's going to be, again, why were we doing this? This was the place where the system would balance. Okay, so that's what we're kind of looking for, the balancing point. And it's this idea of the sum of the moments divided by the sum of the masses. And so without sum of the moment about the origin divided by the sum of the masses. I'm not going to extend that now to the integral. You can read that in your book. I'm just going to tell you that if we can put some integral signs in there, and we're all fine to do that. Okay, so let's look at the first example, which is just a little sort of seesaw question. It says an 80-pound child and a 100-pound child are balancing on a seesaw. The 80-pound child is 5 feet from the fulcrum. How far from the fulcrum is the 100-pound child? Well, you know that you have to set these systems equal to each other. I mean, you have to have equality there. So the mass times the distance, which is the torque, has to be equal on, because we just have two children, we just have to set those two things equal to each other, right? So we've got the, because the children, let me change to blue. Because the children are balanced, the moment of the system about the origin must equal 0. The moments, really the torque, but the torque just has that gravitational pull in it, and it's been divided out. So the moment and so, well, the moment is the mass times the distance. So you're going to do 5 is the distance times the mass, which is 80 pounds, has to be equal to this unknown distance times the 100-pound child. You have to set those equal to each other, or add them together and equal 0. Okay. And so when you compute this, let's see, this is 400 equals x times 100. So you get x is equal to 4 feet, because that was 5 feet. So the distance, and it has to be obviously on the other side. You know, the one child is 5 feet away, but the 100-pound child only needs to be on the other side 4 feet away for the system to balance. So 4 feet from the fulcrum on the other side. So that would be kind of, I think sometimes in science classes they actually have the balances, and you can kind of actually do this problem. It might be kind of fun, but we don't have any fun in here because we're just math. Right? Can you read that okay? Okay. So density, a material's density is its mass per unit volume, but in practice let me see if I can. In practice, we tend to use units we can conveniently measure. And for wires, rods, and narrow strips, we use mass per unit length. And for flat sheets and plates, we use mass per unit area. So, because what we're going to have to think about here is if your wire does not have constant density, how is that going to affect where you can put the center and such? Okay? And so this density function is what we're going to introduce here, this little, it's kind of a delta of x. It's a density function, which will be given in each problem. So it says, the moment about the origin is just going to be the sum of the, remember, it's the distance times the mass. When then you have density to get to the mass, you're going to take the density, which is mass per unit length, and multiply by the area, and this will give you the mass. And then this is the distance that you are away. And that if you sum these or give the integral, that will give you the moment. Now, the mass itself is just going to be this density times at every increment. If you multiply the density times the length, you're going to get back to area. If it's, to mass. If it's mass per unit length, and you multiply mass times length, the dx is like a length, then you're just going to be done. You're just going to have mass left over. And then this integral sign is just going to sum the masses. And then based on that function that we just derived, the center of mass is the moment about the origin divided by the mass. Okay, so again, I'm working a little bit to try to get you to understand the formulas, but in actuality, the homework questions are going to be just applying the formulas or using the formulas and kind of give you a sense of how to do it. Okay, so let's look at examples 2 and 3. See if this is a little better. It says, find the moment about the origin, the mass, and the center of mass for a thin rod with given density and interval of the x-axis. Okay, so these are our 2 examples that we're going to work on. I'll give myself lots of room. Okay, so according to the formulas, the moment about the origin is equal to the integral from a to b of x times the density of x dx. Okay, so for this problem, this one's actually pretty easy because we have what's called a constant density. Our density function is just 4, right? So the moment about the origin is going to be the integral from 0 to 2, and we'll have an x, and I'll go ahead and put it, and then our density of x is 4, and then we have a dx. But I'm going to write that a little bit prettier, right? Okay, and so how does this integrate? This integrates to 4x squared divided by 2. You're going to evaluate that from 0 to 2. And if you, the 2 goes into 4 2 times. 2 squared is 4. So, and then the 0 is just 0. So this is going to be 8. So your moment about the origin is 8. That, because you're not seeing. What's recording? I'm sorry. Is that good? I'm sorry. There. Now you can see it.
Okay. Yeah, I can see the whole thing.
I'm sorry. I'm kind of jumping around there. What you see and what the machine sees are different, and so I have to get it right. Okay. All right. So now let's look at what the mass is. All right. The mass. So this was the moment about the origin. Now the mass is the integral from a to b, and all we have to do is increment. We just take the density and multiply it by a little segment, and since density is per unit length, mass per unit length, when you multiply by a unit length, you're just going to end up with mass, and then you sum them up, you're going to get the total mass. And so this will be the integral from 0 to 2 of 4 dx, which is, of course, it's just 4x from 0 to 2, or 8. Okay, so both our moment about the origin and our mass is 8. Now, if you're having a good day, all right, and I had started this question without even looking at the formula, and I told you that it had constant density, and we're considering it on the interval from 0 to 2, could you tell me what the center of mass was, where the center was? Can you feel the center of this rod? You can? Where do you feel it to be? The rod lies on the interval from 0 to 2, right? This is 0 and this is 2, and it has constant density. So where is its center? It's centered at 1, right? Just right in the middle, because it's not very interesting. It doesn't have very interesting density, right? Well, that's exactly what's going to happen when you use the formula because the formula for the center of the mass is the moment about the origin divided by the mass, which is just going to be 8 over 8, which is just 1. And that's because we're from 0 to 2, the center, the middle between 0 and 2 is 1. Now, this is only true because we have constant density. This 4 here, is describing its density. Okay, so the center of the mass is this divided by this, the moment divided by the mass, which is 8 over 8, also known as uno. Okay, so that, go ahead.
As long as it's any just number, it's going to be center of one.
Well, it had to do with where it was on the x too. Like if it was from 0 to 5, then it would be at 2.5. It's at the midpoint when it has constant density. But of course, most of the problems aren't going to have constant density, so you have to think a little bit. And then what we're going to do at the end here is we're going to, towards the later examples, we're not going to be just looking at thin rods because that's not very exciting. We're going to take flat planar plates, and then we're going to have an x and a y. But if it's symmetric about one of the axes, then one of the coordinates of its center of mass will be the average, will be intuitive. The other one.
Your conference is scheduled to end in 2 minutes.
I hope they fix that. Okay. All right. So now let's look at number 3 because it's a little bit more exciting. On number 3, we're going to have. We have a density that's defined differently. Brandon, are you still there? Because it says I'm the only participant.
I'm still here.
Okay, good. All right, so here we are on number 3. And we'll be just going through the problem here. The moment about the origin is the integral from a to b of x times the density of x dx. So in this case, it's going to be the integral from 0 to 4, and then you have the x, and then the density is 2 minus x over 4, and then dx. Okay, and so this is just going to be a little integration fun. We'll integrate from 0 to 4, and this will be 2x minus x squared over 4 dx. And so this is, hey.
Class in here at 9:35.
This is my class. I think that this is Cal 2, 2414. I know Annette Scott has, are you broadcasting?
No, and I can't. I don't know why they put me here.